Welcome back from the lunch. I hope you had good lunch and come back with full energy. So we have three more talks for today, and among three, one of them will be video talk, virtual one, because Professor Devis Tuia could not make it due to personal reasons. He was supposed to be flying today, but he could not make it despite unforeseen circumstances. He was kind enough to record a video and send it to us. So we'll be playing a video of about half an hour. We'll watching that video, and then he has mentioned in the video that if you have any question, you can reach him out directly with his email address. So let's let's start with the video, please.
Hello, everyone at the workshop. Sorry for not being there. I had, unfortunately, to stay in Switzerland for dealing with some personal important matters. So I would have loved to be there with you and share all the excitement about foundation model for you, but that's how it went this time. I still wanted to share with you the content of my talk. I know online talks are not great, but I think it might be interesting for you to sit down this half hour with me and just see what I wanted to tell you about our research. I hope it's nice, and feel free to reach out if you have any questions after the talk. Okay, let me share my screen now, and let's get started. Here we are, and let's go. So the talk is named A Matter of Smarties because we're going to talk about two papers, two models. One is called Meteor, the other is Smarties. I thought it was funny, but in the end, it's a kind of a gentle walk in our first investigation towards foundation models for EO in my lab at EPFL. I hope you enjoy the ride. Let's go. Basically, I just stole a definition of foundation model I found in the slides of a colleague, and basically, foundation models sometimes are defined as well-pre-trained models that can be fine-tuned with a reasonable amount of data and compute. So this definition is pretty generic, and also when I see that, I was like, hey, wait a second. I mean, that's what I've been doing in the last 10 years, right? We take a model that is trained on some data, for example, ImageNet, so it's not remote sensing, like the one you see at the bottom, and then you modify the inputs and the outputs, so you start throwing in some remote sensing images, and then instead of predicting cats, dogs, and boats, you start predicting, for example, land cover classes. Okay, I think we need a little bit of a more detailed definition, as also my colleague did. This was the beginning of his talk, and he ended up with a definition that sounds like that. So it's neural networks that are well pre-trained on large, diverse data sets with self-supervised objectives, and then they can be fine-tuned with a reasonable amount of data, not too much, because otherwise, why do we do large-scale pre-training? And we don't need too much compute, and we need a small head. So what is this small head? Let's have a look. So I will now take the figure below that is the same as before and just compress it so we make some space. So just in the three dots here, we have all the model basically, and we get to a representation. So what is a small head? Basically, a small head is what the model is doing, right? And these models can work in a multitask setting. So we can have, for example, a head, a decoder, and then classifier that will classify land cover. We could have a detection model that would, in this case, detect trees, for example. A head that does land cover classification or land use classification at the entire scene level. And this is the story of the small heads. So we have these big models that give you the representation, and given this representation, you can tune a small model, then solve a specific task, or many of them at the same time, as in the example here. The other part of this definition that was not in the original one is the large, diverse data sets. And this is also something that foundation model have been leveraging, and that's why they're so good at what they do, is that when we pre-train them, we don't use just one data set, but we can use multiple. And depending on the design, we can also learn across sensors, and we will see this in the second study called Smarties. Okay, so after this short introduction, well, we will have two parts today. The first is called Meteor, and we will see how we can learn across tasks. So it's if you want the multiple heads part, when you don't have a lot of compute and maybe very small data sets, and so it's not yet foundation model. It's more like how can we do with the technology we have without using a foundation model. And then the second part, which is called Smarties, it's where we embrace the foundation model, and we will discuss a little bit how to do multi-sensor, multi-model pre-training, how to train that, and how to add new sensors if you are missing one. I've added a couple of pictures generated by GPT-4. I thought it was funny. So this is what GPT-4 thinks a Meteor of Smarties is. Okay, let's start with Meteor. So the story is to bringing gaps across downstream tasks. And we want a model that can learn to adapt rather than learn to solve a specific task. It's a paper led by Mark Roosworm, who is now in Wageningen, and collaborating with a lot of very smart people, Sherry, Benjamin, Ribana, and myself. And you can find it open sourced on Nature Communication, Earth and Environment. All right, so okay, now these days we like to make big models, right? But I mean, the leitmotif of this presentation is that we don't forcibly have to go bigger at all costs. Also, because some of us don't have the amount of compute necessary to mimic in the industry large scale foundation models. Okay, and also it's not just a problem of compute, but it's also sometimes a problem that our downstream tasks do not have so many training points. So if you have a very niche application where you have some very well acquired, very important samples, maybe they're not enough to learn a fully fledged neural network, but you still want to use them. And this is where an approach like Meteor comes in. Okay, we want to imagine to scale across this problem by doing some fine tuning done well. So the idea is this big this big flow chart, but basically you could see this as a two steps adventure. Okay, the first step of the adventure is to learn the meta model, so which is here in red, and the second part is to take this meta model and to learn task specific models that will address different types of downstream tasks. Okay, oh, I know it sounds a little bit like fine tuning, like you learn a representation and you tune it to your problems, but this is a little bit more thought of, and we'll also see how we go back and forth between the meta model and the task model. But in the presentation, you will always see the same red box for the meta model and gray box for the task model. So it's easy to follow. So part one is how we learn this meta model. And the job of the meta model is basically to learn how to jump from one task to another with minimal supervision. Okay, so it's a little bit different than having a model that is trained to solve the problem itself by massive training. Okay, so to learn a meta model, by the way, we use the MAML framework, just that I forgot to tell you. But to learn a meta model, what we basically do is that we take a land use land cover dataset, SEN12MS, and we split it in a lot of smaller tasks. So you remember we started for the principle that the downstream task will be small and with not so many training points, and they will always be different. Okay. So in the pre-training, what we do is that we take SEN12MS, we split it first by location, and then at each location, as you can see here, we have USA, then Chile, then Europe. We will split every one of these subparts into training and test set. And in each one of these sets, which are made just by a handful of examples, like in this case, we have 4 examples for the training set and 4 examples for the test set, we will do one against all classification. So in this case, we're trying to classify water versus all the other classes in the train and in the test set. Then, when the next task comes in, it's going to be in Chile, so different location, and then the task will be urban versus all the rest. Then in Europe, again, train and test is going to be cropland versus all the rest. And we will keep changing locations, dataset, and which class is classified against the others. And by doing that, we're basically learning a representation, a pre-trained representation that is very good at shifting with very, very little training data. When we have the meta model, then it's time to learn the task models, which are basically models that specialize in single downstream tasks. So the meta model, the red one, it's one. The task model, you will have one per application. Okay? So in this case, we will use this type of flowchart. So we always start from the meta model. We make a child model, that is the task model, that is identical to the meta model, and then we tune it with a training set from the downstream task. We evaluate on the test set, and we keep on going, like the usual fine-tuning loop we have for the task model. But when the task model is learned in our objective, we also have an update of the meta model that then gets better and better by learning more and more tasks. So in a way, the pre-trained meta model keeps growing by learning from the different task model. And this is very powerful because it also helps the meta model to modify itself and get better depending on which task it is confronted to. So this is like the strategy of MAML, which is by Finn et al. And this is the base strategy that we use. We make two big modifications. So first of all, since our problems are multi-class, well, we will run all the classes for the task model at inference time, and then try to predict each class separately. And then at the test time, we will run all this one versus all classifier, and then finally classify by maximum probability of class membership. The second difference that we do is that the meta model is pre-trained with a superset of sensors. So in this case, we had Sentinel 1 and 2, and so we learn the model with all the bands. And when we initialize the task model, we will initialize only with the filters that the sensor specific to the task has. Okay, and this allows us to, in a way, be able to tackle different tasks with different sensor, in our case, Sentinel-1, Sentinel-2, and RGB sensor. Okay, some results. I mean, I know it's a big table, but let's just look at the important part. So we have 1, 2, 3, 4, 5, 6 data sets that you can see here. They have different spatial resolution from 10 meters to less than a meter, different bands, Sentinel-1, Sentinel-2, both RGB, and they vary also in number of classes. As you can see, the number of training images is very, very low. So we start from the principle that the downstream tasks we are interested in do not have a lot of of labels. And this is also why a model as simple as Meteor works well and makes a very good job, as you can see here. If you just look at the ranking with the different approaches we have compared with, on average, we are with Meteor doing the best job. Of course, it's not always the best, and this is not really important. The important part is that we can tackle all these tasks with the same meta model just by learning a task model with a handful of images. And I think this is very powerful, and this is what is interesting with Meteor. Then, since we have this representation, then as for any modern foundation model, you can use this representation to do semantic segmentation, for example. And here is just an example that we have in the paper when, with the same meta model, we initialize a task model whose task is not classification this time, but semantic segmentation. In this case, we are looking at floating debris in the oceans with only 5 training images and the corresponding labels, so annotation masks. We can then get to some predictions that are totally correct, and yeah, that's it. Okay, so for Meteor, for concluding, I will say that it allows you to move from a one model, one task paradigm using meta learning to something where you can adapt to different tasks, and that's maybe a precursor of foundation model, but it's also something that can be tuned just with a handful of tuning example, and I think that's very cool. Of course, it has its limitations. So for example, our pre-training set was one data set, SEN1 to MS. So we could have a more pre-trained data set using more sensors. But of course, I mean, this is what I'm going to present you in the second part with Smarties, and where we really have tried to jump into the foundation model wagon. So if you're interested, Mark gave a very nice introduction to Meteor. You have here the link. You can get the code. You can try it. This is as usual with our works, completely open source. Okay, I hope it's going well. That you're still enjoying it. Let's talk now about Smarties. So Smarties is our first foundation model, let's say, and it's a work that we're gonna present at ICCV in a month from now. It's a work led by Genjer Sumbul and with all colleagues from the lab, Changsu, Emanuele Del Sasso, and myself. As you can see in this image, the idea is to invite more sensors to the party, even though maybe you haven't seen them during pre-training, but they still want to be used and they want to be happy as the one on the right, listening to music and having beers. So basically, it is our foundation model for multimodal remote sensing. Okay, so in this foundation model universe that you will see a lot during the 3 days of the workshop, there are many models that are fantastic. I mean, they all work very well, and I think you can always find one thing that one is missing with respect to the other. Some are sensor specific, some are very complex and require a lot of data and parameters. Some require massive pre-training set. I mean, you can always find a problem with one of the other. In our work in Smarties, we try to tackle those by having a unified image representation for the diverse EO data, so a multimodal foundation model that can also expand the sensor it has been trained on. Because we know that our sensors are very different. If you go on high resolution RGB, multispectral data, SAR data, I mean, they see very different things. They have different resolutions, different bands, and it will be very nice to be able to compensate the weakness of one with the strengths of another. And since nowadays we start to have a lot of collocated data, that's probably something that we can leverage. And so this is why we thought about Smarties. I like to see it as a kind of a signal powered, you could say, like spectrum based foundation model, so that we really try to leverage our knowledge of signal processing and of the physics of the spectrum by having a model that will try to project all the bands that you have, which are very well defined in terms of frequencies and signals, into a spectrum aware space. So we try to align those bands in this space, so that the sensors, when they are aligned, they will give you the similar information. And then when we have this aligned representation, we will have a single transformer model with a self-supervised objective that will do the magic for us. So the flowchart looks like that. Don't worry, you don't have to understand it right now, because I will go through it piece by piece. Let's start very, very simple. Let's say that we have some sensor data at the entrance, some Smarties. Each color corresponds to a band, because the spectrum, it's always represented by different colors. Then we will have some kind of model in the middle where it will shake it, and then the idea will be to reconstruct the same data that have entered the model. So it's a reconstruction objective. It's something that it's very popular. It's going to be some masked modeling, you will see, and now let's see the details more maybe more serious way than than this little jokey start. Okay, we have three parts. The first part is what we call the spectrum-aware image projection. So we'll try to project our sensor data into sensor-specific tokens. Then in the second part, we will have a cross-sensor mix-up to increase the robustness of the approach. And when we have our mixed tokens, then we will do the transformer part, which is a third, and is the spectrum-aware image reconstruction. So part one, spectrum-aware image projection. So as you can see here in the diagram on the top left, what we will do is that we will take every band, and every band will have its own projector, and it will create a representation which is frequency specific. And then each one of these projection will be averaged for a single sensor, and it will create a sensor-specific token. Okay, so let's say in this example, we have a multispectral patch, a SAR patch. So this will lead to two tokens, one for SAR in blue and one for multispectrum in yellow. The functions are learned during learning, and they will be specific to a given wavelength. In the second step, the cross-sensor token mix-up, what we will do is that basically we will take pairs of aligned images, so images from two sensors looking at the same place at the same time, as much as possible, and then we will exchange the tokens across the image pair. Okay, so as you can see here, at the beginning we have a tokenization of the first sensor, a tokenization of the second, and we will, exchange some of them so that the model gets a little bit of a more difficult job, and it needs to learn better cross-sensor representations. And then in the third step, we will have our tokens map, and now we will take the tokens and do the reverse process. So from the token, we will re-separate into the representation per wavelengths, and then reconstruct the original bands. The comparison with the reconstructed bands with the original ones will be our learning signal. Now, one thing that I didn't tell you yet is how we deal with bands that the model has not seen during pre-training, because that was the objective. You remember the satellite that wants to join the party. So in Smarties, which is our first attempt at this, we went with an approach that will be an averaging of the closest representation of the bands that are closest to the one being discovered by the model. Okay, so it's a weighted average of these bands that are close by, and this will become the token for the new sensor. Okay, and this allows us to interpolate within the spectrum in bands that we maybe have not seen. Okay, some experiments now. So we pre-train of more or less 500,000 pairs of images. They come from functional map of the world, the version RGB or the version Sentinel-2. That's 120,000 pairs. Or we use big EarthNet multimodal with 370,000 pairs of images, and this time Sentinel-1 and Sentinel-2. We pre-train two models. One is the base, one is the large backbone for 300 epochs, and the models are more or less of the same size of multi-MA. And for downstream task, you will see we will have different sensor, different task, segmentation, classification. There is a lot of them to have fun. Okay, let's start with the big table that you can find then in the paper. Here we are looking at the multimodal performance. We will first see the performance on single sensors, like here, and we are training on 10% of the bigger net dataset. So in this case, as you can see, we are performing as good as all the other recent foundation model, which know Sentinel-2 pretty well because they have been pre-trained on it. So remember, in this case, we are using only Sentinel-2 downstream task, but of course, Smarties is trained on all the sensors at the same time. Also, when we use larger backbones, we get good performances, better. We're very close to Chroma, but just remember that we're using just a quarter of the Sentinel-2 data that has been seen by Chroma. So I think it's good performance for smaller pre-training sets. Now, story become very interesting when we start to look at Sentinel-1. In Sentinel-1, the performance gap with most models increases, which is great. So in this case, we're using only Sentinel-1 for our inference, and yeah, now we start to see some large gaps that become even larger when we then use the multimodal data set. So in that case, we are looking at Sentinel-1 and Sentinel-2 at the same time. So we're using this cross-sensor mix-up for learning, and that's where the model really shines, as you can see. Um, we also looked at different scenarios. So, for example, we're looking at this interesting experiment that was done in TerraMind, where they were using only 10 images, one per class, and then doing some feature mapping with the query set, which is in this case the the full data set, and here we see that by using Smarties, we are basically again improving several of the current foundation models, and we are behind TerraMind by a few percentage point. I mean, I I attribute that to the fact that our pre-training data side it's strongly smaller, so we're talking a 500,000 images versus 64 millions, or even the number of parameters of the model. So I will say for a very small models like Smarties, we are doing a remarkable job. Then we looked into robustness with respect to scale on different data sets as downstream tasks. So, for example, VURS 19, we are competitive, in Merced as well, across the scale. So we predict for the different scales and then we average. And then we are also looked at Resist 45 and even comparing with the state of the art that has been as has seen this data set during pre-training, we have basically not, and we only have 60,000 images at that resolution. It's not even the same data set, and I think we're doing a remarkable job. Then semantic segmentation, as I told you, you can plug in another model when you have learned your feature after the encoder. In this case, we fine tune UperNet, and then we can tackle different data sets. We took those from the Pangea benchmark, and Smarties is performing remarkably well on all of them, despite not having done any semantic segmentation so far. And finally, I think this is the last experiment. We wanted also to see how it performs when we confront Smarties to a new sensor it has never seen before. In this case, it's Landsat, so it's a sensor with thermal bands, and the model has never seen thermal bands before. And and I'm happy that Smarties works very well and improves on fully supervised UNet and Deep Lab. Sorry for the typo. And of course, I mean, without the interpolation, so by ignoring the thermal bands, Smarties is working that's well, but this is totally expected. And I mean, for me, it just tells me that it can learn something useful from the thermal bands, even though he has never seen one. Okay, I hope it was interesting. I hope you enjoyed the talk. For my main conclusion is that foundation models do not forcibly have to be big, but they must be smart. And in our case, I think that we have been looking first at Meteor, which is not a foundation model, but still tries to leverage this idea of making the most of the data that you have. And then Smarties, it expands on it by looking at this multi-sensor, multitask, multimodal approach by taking into account that we know about the electromagnetic spectrum. So if we create spectrum-aware projection, we can basically increase efficiency and performance. You have here in the QR code model weights, code, everything you want. I hope it's not covered by my my little image, but it probably is. If so, I'm sorry. Let's try to remove it. Maybe it comes like this, you can see it better. I don't know. But if you haven't, well, you can just search for Smarties and EPFL, and you will find it. If you're around in Hawaii at ICCV, we will be very happy to discuss all this with you. What's next for us in foundation model for Earth observation? Well, I really want to push this idea of integrating more physics into foundation model for better generalization across modalities. I want to work more on unseen sensors and downstream transfer, and try to make it more and more compelling and usable for everybody. Now we have started an European project, a Horizon project called DVPS, Diversibus Vis Plurima Solvo. And here you have the website if you want to have a look. It's just starting, but it's a really cool project with a lot of very, very interesting partners. Okay, that's it, folks. I enjoy a fantastic conference. If you have questions, just drop me a line and I'll do my best to reply. I hope it was a good experience. Let me stop sharing so I can see you goodbye properly, and take care, have fun, and see you soon somewhere at a conference or something like that. Take care.